Welcome to another episode. Let me know where you're listening from and what time it is there. And if you enjoy drifting through science and wonder, consider subscribing for more. Tonight, we're going to explore the invisible forces that shape everything, from the way a ship floats to the way galaxies drift apart. This isn't just about formulas or numbers. It's about understanding the rules behind reality, the physics that guides motion, balance, light, fire, and even space itself. So settle in, let your thoughts slow down, and let's follow the forces, from the tiniest friction to the farthest stars. Imagine a ship, a floating city of steel, weighing over 200,000 tons. By all intuition, this mountain of metal should sink. It is heavier than water, denser than the ocean it sails through, and yet it glides on the surface with grace. This paradox has puzzled minds since the earliest days of human curiosity, and it leads us to one of the most fundamental principles in physics: buoyancy. Long before equations, before Archimedes took his famous bath, humans had already observed floating. Leaves drifted on rivers, logs bobbed in lakes, and oil spread on water's surface. But observation alone doesn't always lead to understanding. Why do some objects float and others sink? And why, sometimes, can an object heavier than water, like a ship, still remain afloat? The answer is deeply tied to density and displacement. Every object has a density, mass per volume. Water has a density of about 1 gram per cubic centimetre. If an object's density is less than water's, it floats. If it's more, it sinks. But this simple explanation doesn't capture the full elegance of the phenomenon. To see it clearly, we need to travel back to ancient Greece, to the city of Syracuse, around 250 BCE, where a mathematician named Archimedes was tasked with solving a king's suspicion. King Hiero had given gold to a craftsman to make a crown. The crown returned was beautiful, but the king suspected the goldsmith had cheated him, mixing silver into the gold. Hiero asked Archimedes to prove whether the crown was pure without destroying it. The story, perhaps embellished over centuries, tells that Archimedes stepped into a bath and noticed the water rising as his body sank. The displaced water weighed exactly as much as the portion of his body submerged. In that instant, the idea struck him: the upward force on a submerged object equals the weight of the fluid displaced by it. Overjoyed, he supposedly ran naked through the streets, shouting, "Eureka! I have found it." Whether or not this scene occurred exactly as told, the principle he discovered is still taught in every physics class today. This upward force, now called the buoyant force, is what allows a ship to float. Even though the steel it's made of is denser than water, the shape of the hull ensures it displaces a volume of water whose weight is greater than the ship's weight. This displaced water pushes back, holding the vessel up. But buoyancy doesn't stop at ships. Think of a submarine. It can sink or rise at will by adjusting tanks that fill with water or air. When filled with water, its overall density increases and it sinks. Pump in air, decrease density, and it floats. This balance is a delicate dance of physics and engineering. Now, consider a simple experiment you can do at home. Drop an egg into a glass of water. It sinks. Add salt, stir, and try again. As the water's density increases due to dissolved salt, the egg begins to float. Here, the salt water behaves like the dense waters of the Dead Sea, where even the least buoyant human floats effortlessly. The principle of buoyancy reveals itself in countless places. A life jacket works not because it makes you lighter, but because it increases your effective volume while adding very little weight, reducing your density. An iceberg floats with most of its mass hidden underwater, its tip only a silent warning of the bulk below. There's even a poetic interplay of buoyancy in the sky. Air, like water, is a fluid. Hot air balloons rise because the heated air inside the balloon expands, becoming less dense than the cooler air outside. The surrounding air pushes up with a buoyant force, and the balloon lifts. You are surrounded by buoyant forces at every moment, though you rarely think of them. Physics, at its best, doesn't just explain, it surprises. There are curious cases where buoyancy seems to behave counterintuitively. For example, a boat loaded with a heavy anchor floats at a certain waterline. Drop the anchor into the water, not on the bottom, but suspended from the boat, and the boat sits higher. Why? When the anchor is in the boat, it adds to the boat's weight, requiring more displaced water to balance. Once it's hanging in the water, its weight is partially supported by the water itself, so the boat displaces less. These small twists make physics endlessly fascinating. And then there are the extremes. On Titan, Saturn's largest moon, lakes of methane and ethane exist at frigid temperatures. These liquids have densities lower than water, and scientists speculate on how different materials might float or sink there. A spacecraft probe could use buoyancy principles to float on Titan's seas, just as Viking ships did on Earth. Buoyancy even extends to the microscopic world. Tiny particles in a fluid undergo Brownian motion, jiggling under the influence of surrounding molecules. Some particles float in suspension, neither sinking nor rising quickly, their behavior governed by an equilibrium of forces at a scale we can barely see. When engineers design floating cities or futuristic habitats on water, they revisit Archimedes. When scientists study how ice sheets melt and float, they apply the same principle. Even icebergs, floating with 90% hidden below water, obey the same laws Archimedes described over 2 millennia ago. Floating also links to stability. Why does a ship right itself after tipping, while a capsized one stays overturned? This involves the metacenter, an imaginary point where buoyant forces act. If the metacenter is above the center of gravity, the object stabilizes. If not, it flips. Designers obsess over this balance to ensure ships survive storms. Of course, buoyancy doesn't always win. A boat overloaded with cargo can lose this balance and sink. The tragic story of the Titanic reminds us that even with buoyant force at play, other factors like damage, flooding compartments, or human error can defeat physics. There's beauty in how a simple principle explains such a vast range of phenomena. The same law governs a child's rubber duck, a supertanker, and a balloon floating toward the sky, and it doesn't care about scale or purpose. Buoyancy is impartial. Reflect on this the next time you see something float. Beneath the calm surface lies a force as old as nature itself, described in a Greek bath, powering the dreams of sailors, engineers, and scientists. It is the quiet hand that holds things up, the unseen push of water and air against the weight of the world. When you drop a leaf into a stream, it drifts. Not because it is magical, but because nature has a way of balancing weight with the pressure of the surrounding fluid. It's a reminder that even the simplest phenomena are rooted in profound truths. And perhaps, like Archimedes, you might have your own quiet eureka moment when you notice how the world holds things afloat. In the stillness of water, physics whispers its secrets, patiently, elegantly, waiting for you to listen. If buoyancy is the unseen hand that lifts objects, friction is the quiet force that holds them in place. It is everywhere, yet so often ignored, until it is gone. Imagine walking on a perfectly frictionless surface. No matter how hard you tried, you wouldn't move forward. Your feet would simply slide, helpless. Without friction, wheels wouldn't turn, brakes wouldn't stop, and life as we know it would be unrecognizable. At its core, friction is the resistance that one surface encounters when sliding over another. For centuries, philosophers and scientists puzzled over what caused this invisible grip. Aristotle believed a heavier object created more friction simply because it pressed harder on a surface. While partly true, the real story is subtler and far more interesting. Friction originates from microscopic roughness. Even the smoothest surfaces, glass, polished metal, are not perfectly smooth. Under a microscope, they reveal peaks and valleys like tiny mountain ranges. When two surfaces meet, these microscopic peaks interlock. To move, you must overcome this interlocking, which takes force. This is why friction is proportional to the normal force, the perpendicular push between surfaces. The harder two objects are pressed together, the more those tiny peaks interact, and the more friction resists motion. This principle is so consistent that it became one of the earliest laws of physics, described by Leonardo da Vinci and later formalized by Guillaume Amontons in the 17th century. Yet, friction isn't just about roughness. Modern science shows that at the atomic level, there's more at play. Molecules from one surface can attract molecules from the other through electromagnetic forces. These interactions create additional stickiness, especially when the surfaces are very clean and smooth. The coefficient of friction, often written as mu, quantifies how much friction exists between two surfaces. Rubber on asphalt has a high coefficient, giving car tires grip. Ice on steel has a very low coefficient, making slipping almost inevitable. But why is ice so slippery? For years, scientists believed that pressure from your foot melted a thin layer of water on ice, creating a slick surface. Others argued it was frictional heating from sliding. While both play roles, recent research reveals something more surprising. Even at temperatures well below freezing, the surface molecules of ice form a thin, liquid-like layer. This layer acts as a natural lubricant, making ice dangerously smooth. On an atomic scale, the outermost molecules of ice are less tightly bound and behave like a microscopic liquid film. This explains why ice skaters glide with such ease, even when temperatures are far below zero. Skating itself is a fascinating display of friction's duality. The thin water film reduces friction, allowing smooth sliding, yet there is still enough friction for the skater to push off and gain speed. Without this delicate balance, skating would be impossible. Everyday experiences reveal friction's complexity. Rub your hands together, they warm up. That warmth is energy, the mechanical energy of motion transforming into heat. This is why car brakes can glow red during intense use. The friction pads convert the car's kinetic energy into heat, slowing it down. Without friction, stopping would require entirely different mechanisms. One of the most famous experiments involving friction dates back to Galileo. By rolling balls down inclined planes, he discovered that friction was the culprit that slowed objects. In an ideal world without friction, a ball would roll forever. This realization paved the way for Newton's first law of motion, the principle of inertia. Modern science continues to explore friction at astonishing scales. In nanotechnology, engineers face a challenge. As machines shrink, the ratio of surface area to volume increases, making friction far more dominant. Tiny components can literally stick together due to surface forces, halting their function. Understanding friction at the atomic level has become essential for creating micromachines, hard drives, and even advanced spacecraft components. Friction also creates strange phenomena. Stick-slip motion occurs when two surfaces alternately stick together and then suddenly slip, producing a jerky movement. This happens in violin bows, giving the instrument its voice, and in earthquakes, where tectonic plates lock and then release energy catastrophically. Speaking of earthquakes, the largest ones occur where friction holds immense slabs of rock together until the stress becomes too great. When they finally slip, the energy released shakes the ground violently. Here, friction is both a protector, preventing constant sliding, and a danger, storing potential energy until it erupts. There's also the curious case of superlubricity, an almost frictionless state observed when two crystal lattices slide over each other in perfect misalignment. In certain conditions, the atoms do not interlock and friction drops close to zero. This discovery, still being studied, could revolutionize how we design machinery. Let's return to something more familiar. Your shoes. The soles are designed to maximize friction on typical surfaces, using patterns that grip uneven terrain. On ice, however, the coefficient of friction is too low, and you slip. That's why winter tires have deeper grooves and special rubber compounds to maintain grip. Even more fascinating is how friction can behave counterintuitively. For example, when you drag a heavy box, it's harder to start moving than to keep it moving. This is because static friction, the resistance to the start of motion, is generally higher than kinetic friction, the resistance during motion. Once the box starts sliding, the interlocking peaks break, and less force is required. Now consider air resistance, technically a type of friction between an object and the air it moves through. Air seems light, almost nothing, but at high speeds it behaves like a powerful force. Airplanes are designed to minimize this resistance, while parachutes maximize it. Without air resistance, a feather and a hammer fall at the same rate, as demonstrated by astronaut David Scott on the Moon. In a world without friction, wheels would spin without traction, nails wouldn't hold wood, and even walking would be impossible. Friction is the quiet partner in every movement you make, a force you rarely notice until it fails you. And sometimes friction reveals hidden wonders. Have you ever tried sliding a book across a table only to notice it slows and stops? That simple observation is physics in action. Energy isn't lost, it's transformed. The book's motion becomes heat in the table and air, warming them slightly in a way too small to feel. Even in the stillness, energy is conserved. There's also an element of artistry in how friction is manipulated. Think of rock climbers using chalk to increase grip, violinists using rosin on their bows, or chefs sharpening knives on rough stones. Each case is a dance with friction, increasing it where control is needed, decreasing it where smoothness is desired. Friction, like buoyancy, is universal. It governs the movement of tectonic plates, the orbit of satellites, gradually slowed by atmospheric drag, and the simple joy of sliding on a playground. It is the unseen thread connecting the smallest gesture to the largest forces shaping our planet. So next time you slip on ice or feel the warmth of your hands after rubbing them together, remember, you are experiencing one of nature's most fundamental forces. It's not just resistance, it's the force that shapes motion, heat, and even the trembling of the earth. Friction doesn't shout. It whispers in the grip of your shoes, the hum of a violin, the slowing of a rolling ball. And in those whispers, physics reveals its secrets, patiently, elegantly, everywhere. Close your eyes and picture a swinging pendulum, a simple weight suspended by a string, swaying back and forth with hypnotic regularity. It slows eventually, but only because friction and air resistance sap its energy. In a perfect world without those forces, it would swing forever. This never-ending movement is an echo of one of physics' most beautiful ideas, momentum. Momentum, at its simplest, is the product of an object's mass and velocity. It's not just how fast something is moving, but how much oomph it carries with that movement. A ping-pong ball can move at blistering speed, but it won't dent a wall. A slow-rolling bowling ball, however, can crush pins with ease. This simple concept underpins everything from billiards to space travel. To truly appreciate momentum, we have to talk about conservation. The law of conservation of momentum is one of physics' most sacred principles. In an isolated system, where no external forces act, momentum stays constant. This means momentum is never lost, only transferred or transformed. And that single truth explains an astonishing range of phenomena in our everyday world. Consider the classic Newton's cradle, those desk toy spheres hanging in a neat row. Lift one, release it, and it strikes the others, sending the ball at the opposite end swinging out. Lift two, swing out. It's mesmerizing, but more importantly, it's a perfect illustration of momentum conservation. The energy and momentum from the first ball travel through the line almost undiminished, emerging at the far end. But momentum isn't only about neat, orderly demonstrations, it's also the force behind the chaos of collisions. In car crashes, for example, the immense momentum of moving vehicles must go somewhere. Crumple zones in modern cars absorb and distribute this energy, protecting passengers. They don't reduce the momentum, they simply control where it goes. Let's step back to the early thinkers. Sir Isaac Newton, in the 17th century, laid the foundation for understanding momentum with his laws of motion. His second law, force equals mass times acceleration, F equals ma, tells us that any change in momentum requires a force over time. The longer you apply a force, the more momentum you can change, which is why airbags are so effective. They increase the time over which your body's momentum decreases, reducing the force you feel. This interplay between time, force, and motion is visible in sports. A baseball player doesn't just hold the bat still and hope the ball transfers energy. They swing, extending the time of contact, maximizing momentum transfer. A soccer player cushions the ball with their foot to slow it gently, spreading the momentum change over a longer period. Physics quietly rules the playing field. Momentum conservation also drives some of the most spectacular natural phenomena. Think of a meteor hurtling into Earth's atmosphere. Its mass and velocity give it staggering momentum, enough to release energy equivalent to multiple atomic bombs upon impact. The extinction of the dinosaurs, scientists believe, was triggered by such an event, a chilling reminder of momentum's power. And yet, momentum can also create delicate wonders. Consider a water droplet falling into a calm pond. It hits, pushes water aside, and forms ripples spreading outward. The droplet's downward momentum becomes circular waves travelling across the surface. This transfer of motion, from falling to spreading, is physics choreographing beauty. Let's talk collisions, because they're not all the same. There are elastic collisions, where objects bounce off each other with no loss of kinetic energy, like billiard balls, and inelastic collisions, where energy is absorbed, often deforming the objects, like cars in an accident. The most extreme case is a perfectly inelastic collision, where objects stick together after colliding, moving as one. A fascinating demonstration of this is the sticky collision experiment with two carts on an air track. When they collide and stick, their combined momentum is exactly the sum of their initial momenta, even though their speeds change dramatically. Energy may have been lost as heat or sound, but momentum remains conserved. The principle extends beyond Earth. Astronauts floating in the International Space Station demonstrate momentum beautifully. Push off one wall and you glide until you grab something. If you throw a wrench forward, you drift backward. No friction, no air resistance. Just pure conservation of momentum in microgravity. This simple rule allows spacecraft to navigate the void. When they eject fuel at high speed, they move in the opposite direction, propelled without air or ground to push against. Momentum also governs the rotation of objects. Angular momentum, the rotational equivalent, explains why a spinning ice skater speeds up when pulling in their arms. Their mass distribution changes, but their angular momentum stays constant, so the rotational speed increases. The same principle applies to planets spinning in space or a diver twisting mid-air to perfect their landing. Curious experiments have revealed even stranger aspects. For example, the self-siphoning bead chain. A long chain in a container can pour itself over the edge and continue to flow as if pulled by an invisible hand. The momentum of the moving beads lifts the rest of the chain, defying expectation. It's a delightful trick of physics that has amazed millions online. Momentum plays an unexpected role in the stability of bicycles. At high speeds, the rotating wheel's angular momentum resists changes in direction, making the bike easier to balance. This is why a moving bicycle can stay upright with minimal effort, while a stationary one falls easily. Even phenomena like rockets recoiling when they fire or guns kicking back when shot are momentum at work. The bullet goes forward, the gun goes backward, equal and opposite as Newton dictated. Recoil isn't a flaw, it's physics demanding balance. In the quantum world, momentum takes on a new, almost mysterious life. Light particles, photons, have no mass, yet they carry momentum. This is why sunlight can exert pressure, ever so slightly pushing on objects. Scientists are exploring solar sails, spacecraft powered by this faint but relentless push of light. Imagine travelling the stars, not with fuel, but with sunlight itself. Perhaps one of the most poetic uses of momentum appears in space exploration. When NASA wanted to send Voyager probes to the outer planets, they used gravity assists, flying close to planets to steal a tiny bit of their momentum. The planets barely noticed, but the probes gained enough speed to journey into interstellar space. It's as if the planets gave them a gentle sling, a cosmic handoff between worlds. Momentum is not just a law. It's a thread weaving through every movement in the universe. From the smallest collision of atoms to the swirling arms of galaxies, momentum is conserved. It's why a spinning star collapsing into a neutron star rotates thousands of times per second. As its size shrinks, its rotation must speed up to conserve angular momentum. Even in human life, momentum is a metaphor. A project, an idea, once moving, tends to keep moving unless resisted. The same principle that guides planets also whispers in our endeavours. Motion, once started, carries on. When two billiard balls collide, or when a comet streaks across the sky, the same law governs both, the eternal balance of momentum. It is impartial, precise, and beautiful. Think about this the next time you see a child swing slowing in the park, or feel the jolt of a braking car. Physics is at work, quietly enforcing its rules. The world dances to these laws, whether we notice or not. Momentum tells us something profound. Nothing moves in isolation. Every push creates a response. Every movement shares its energy with something else. It's a cosmic give and take, a universal choreography that never misses a step. In the quiet elegance of a Newton's cradle, in the thunder of colliding stars, momentum persists. The universe doesn't just move, it moves with purpose, conserving what it holds most sacred, the endless flow of motion itself. When we think of buoyancy, our minds almost always turn to water. Boats float, icebergs drift, and swimmers bob up to the surface. But there's another ocean, vast, invisible, and pressing down on us at every moment, the ocean of air. We live at the bottom of this ocean, so we hardly notice it. Yet it has waves, currents, and its own kind of buoyancy. The same principle that lets ships float on water also governs why clouds hang in the sky, why hot air balloons rise, and why helium balloons seem to defy gravity. The air around us, though invisible, is a fluid. It flows, it exerts pressure, and it can push back against objects. This is where Archimedes' principle, first discovered for water, shows its full power. It applies not just to liquids, but to any fluid, including gases. Any object immersed in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. A balloon floats in air for the same reason a ship floats on water. It displaces a weight of air greater than its own weight. Consider a helium balloon. Helium is lighter than the surrounding air. A typical balloon filled with helium has a density lower than the air it displaces. The heavier air pushes upward with a force greater than gravity pulls downward, and the balloon rises. It's as if the balloon is swimming upward in an invisible sea. Why does helium behave this way? The answer lies in its atomic structure. Helium atoms are light, with only 2 protons and 2 neutrons. Air, mostly nitrogen and oxygen, is made of heavier molecules. The difference is enough that helium escapes the planet's grip over millions of years. It literally leaks into space. Every helium balloon released into the sky joins this slow, irreversible loss. This idea of rising lighter gases isn't new. In 1783, the Montgolfier brothers launched the first hot air balloon over France. They had discovered that heated air is less dense than cooler air. Heating causes air molecules to move faster, spreading out and lowering the air's density inside the balloon. The surrounding cooler air, being denser, pushes up more strongly than gravity pulls down. The balloon lifts, carrying passengers aloft in a way that must have seemed magical at the time. Hot air balloons are perfect demonstrations of physics made visible. To descend, the air inside is allowed to cool, increasing density and reducing lift. To rise higher, more heat is added. Modern balloons still use this simple yet elegant control. There are no engines, just the play of buoyancy against gravity. But buoyant air is not limited to balloons. The entire weather system is driven by differences in air density. Warm air rises, cool air sinks. This creates convection currents, winds, and towering thunderclouds. When you see a cumulus cloud, fluffy and white, seemingly floating, you are watching water droplets suspended by rising warm air. The cloud's base marks where air cools enough for water vapor to condense. The cloud itself is a monument to buoyancy at work in the sky. Birds have learned to use these rising air currents. Large birds like eagles and vultures glide on thermals, columns of warm air rising from sun-heated ground. They circle upward effortlessly, barely flapping their wings, carried by invisible buoyant streams. Even airplanes, though they fly for different reasons, are still subject to buoyant effects. Air pressure differences above and below their wings create lift, and the density of air plays a critical role. At high altitudes, where air is thin, planes need to travel faster to generate the same lift. Pilots must respect the invisible properties of the atmosphere to stay aloft. There's a fascinating twist. Air pressure itself decreases with height. The higher you go, the less dense the air. This is why mountaineers struggle to breathe on Everest, not because there's no oxygen, but because there's less of it per breath. The reduced density also means less buoyant force. At extreme altitudes, balloons stop rising because the air around them is too thin to push up with enough force. Now let's explore something more unusual: liquid air. When air is cooled to extremely low temperatures, it condenses into a pale blue liquid, about 870 times denser than the gaseous form. Drop an object into liquid air, and buoyancy acts just as in water. This reversal, the air becoming a liquid while the object floats or sinks, is a reminder that buoyancy cares only about density, not the identity of the fluid. The concept even extends into space in surprising ways. You might think buoyancy disappears in microgravity, and in a sense it does, because there's no up or down. Yet gases still behave differently due to molecular motion. On Earth, hot air rises and cold air sinks. In space, without gravity, hot and cold gases mix more slowly because there's no buoyant convection. Fire burns differently, forming small, spherical flames, rather than tall, flickering ones. The absence of buoyancy changes the very nature of combustion. Back on Earth, there are stranger examples still. Certain gases are heavier than air, and they sink rather than rise. Carbon dioxide, for example, can accumulate in low-lying areas, displacing breathable air. There are tragic stories of people entering caves where invisible CO2 pools have formed, only to collapse from lack of oxygen. In the 1986 Lake Nyos disaster in Cameroon, a sudden release of CO2 from the lake suffocated over 1,700 people. Here, buoyancy worked against life, trapping the heavy gas close to the ground until it surged outward in a deadly wave. Not all heavy gases are deadly though. Sulfur hexafluoride, SF6, much denser than air, allows for a striking demonstration. Fill a container with sulfur hexafluoride and you can float aluminum foil boats on its invisible surface, just as they would on water. Drop a small object into it and it sinks slowly, as though falling through honey. These experiments feel like magic until you remember the principle at work. Even in an invisible fluid, buoyancy governs motion. Now think of smoke. Why does it rise from a candle but hug the ground from a wildfire? The difference lies in air currents and density. Warm smoke rises, but as it cools, it can spread downward, following the path of denser, cooler air. On a cold morning, you can see your breath linger, because the warm, moist air you exhale is momentarily lighter, then cools and disperses. Bubbles, too, tell the story of buoyant air. In water, air bubbles rise because they are less dense than the liquid, but in a dense gas like SF6, bubbles of air sink. Physics doesn't care whether it's liquid or gas, only which is lighter. Buoyancy has even been proposed as a means for generating energy. Concepts like solar updraft towers use heated air rising through a chimney to drive turbines, producing electricity. Here, the natural buoyant tendency of hot air is harnessed for human needs. The science of buoyant gases also plays a role in understanding the universe. Stars, for example, have internal convection zones where hot plasma rises and cooler plasma sinks. This movement transports energy outward, shaping the star's life cycle. In a way, the sun itself is powered by giant buoyant flows of gas. And then there's the giant planet Jupiter, wrapped in bands of gas swirling endlessly. Convection currents in its atmosphere create storms so massive they could swallow Earth. The Great Red Spot, a storm raging for centuries, is driven by these buoyant flows. The physics you see in a pot of boiling water, rising hot currents, sinking cooler ones, scales up to a planet. Back here on Earth, the physics of buoyant air continues to influence our daily lives. The air we breathe, the weather we watch, the flight of birds, the lifting of balloons, all are connected by this simple law. Yet it remains invisible, working quietly in the background. Next time you release a helium balloon and watch it rise, think of the unseen ocean above you. It pushes, pulls, and flows in ways we rarely notice. But if you stop and watch, really watch, you can see the patterns. A leaf caught in an updraft, a cloud drifting lazily, a kite pulling on its string. Each one is telling you the same story. The air is alive with motion, and physics is guiding it all. Buoyancy in air is like a secret handshake between gravity and fluid pressure. One pulls down, the other pushes up, and the result is a delicate balance that allows balloons to float, smoke to swirl, and clouds to hang in a blue sky. The world above your head isn't empty. It's an ocean, and we're all swimming at its bottom. In that ocean, objects rise or fall not by magic, but by a rule so simple it feels like poetry. Lighter things go up, heavier things go down, and from the drifting of a soap bubble to the ascent of a weather balloon into the stratosphere, this quiet law never fails. In 2016, the world unexpectedly became obsessed with a simple trick: flipping a partially filled plastic water bottle into the air and watching it land upright. The water bottle flip challenge took over schools, parks and living rooms, becoming a viral phenomenon. For a moment, the entire internet was captivated by the silent drama of rotation, gravity, and an empty sports bottle twirling through the air. But behind the viral trend lies a surprisingly deep lesson in physics. That casual, almost silly motion, bottle, spin, land, is a real-world example of rotational balance, moment of inertia, and angular momentum in action. It turns out physics can be lurking in the most unexpected places, hidden behind teenage challenges and internet memes. When you flip a bottle into the air, you're giving it two key things: linear momentum, the bottle travels upward and then downward, and angular momentum, the bottle spins as it moves. Angular momentum is the rotational equivalent of straight line momentum, and it depends on two things: the moment of inertia and the angular velocity. Angular momentum is conserved, meaning it stays constant unless an external torque acts on the object. But here's where things get interesting. While angular momentum remains the same, the distribution of mass can change the moment of inertia, which in turn changes the spin rate. This is where the water inside the bottle comes into play. If the bottle were empty or completely full, it would spin uniformly and quickly, and it would be much harder to land. But with just the right amount of water, typically around 1/3 full, something curious happens. As the bottle flips, the water inside moves. It sloshes upward, spreading along the bottle's length. This redistribution of mass increases the moment of inertia. And according to the conservation of angular momentum, when moment of inertia increases, angular velocity must decrease, so the bottle slows its spin mid-air. This slower rotation is critical. It gives the bottle more time to orient vertically and descend steadily, not wildly spinning, but gently returning to Earth. That dynamic balance, achieved through water slosh, is what makes the trick work. It's not luck, it's physics. This principle, changing spin rate by changing mass distribution, isn't unique to water bottles. It's the same physics that governs ice skaters. When a figure skater pulls their arms in, their body spins faster. That's because they've decreased their moment of inertia. With the same angular momentum conserved, the spin must speed up. Conversely, when a skater extends their limbs, they slow down. The mass is farther from the center, increasing inertia. Less spin. The water bottle does the same thing mid-air. At the start of the flip, much of the water is near the bottom. As it flips, inertia shifts. The water spreads upward, increasing rotational inertia and slowing the spin. It's beautifully analog. No computers, no gyroscopes, just Newtonian mechanics in plastic and liquid. Through testing and experiments, physicists and amateur scientists alike discovered that the ideal water bottle fill level for successful flips is around 25% to 35%. Why not more? A full bottle doesn't allow enough movement of mass. The water is rigid, trapped. It behaves like a solid, rotating quickly and evenly, with little shift in inertia. That rapid spin makes it harder to land upright. An empty bottle, on the other hand, has almost no mass at all at the bottom. It's light and flutters through the air, prone to chaotic motion. It lacks the rotational stability needed to land consistently. But 1/3 full, that's the magic zone. Enough weight at the bottom to create stability, enough free water to slosh and increase moment of inertia, enough variability to slow the spin, align the bottle, and cushion the landing. After the viral trend hit its peak, real physicists started analysing it. A study from the Netherlands even published findings in a physics journal, treating the bottle flip as a serious mechanical system. Researchers modelled it as a rotating asymmetric body with internal mass redistribution. The results were enlightening and surprisingly useful. Understanding how a system stabilizes itself mid-air can inform everything from robotics to aerospace engineering. Rockets, for instance, experience shifting fuel during flight. Managing stability as mass redistributes is crucial to staying on course. The humble bottle flip gives us a sandbox to study these principles. Physics never happens in isolation. The same principles in a flipped water bottle appear all over our lives. We just rarely notice them. Washing machines use rotational motion to spin clothes dry, but when clothes clump to one side, the rotation becomes unstable. That imbalance throws the washer off kilter, a real-world failure of symmetrical moment of inertia. Gymnasts and divers twist and flip mid-air by manipulating their body shape, changing rotational inertia as needed. A diver might tuck into a ball for fast rotation, then extend just before hitting the water to slow and prepare for impact, exactly like our water bottle adjusting itself in flight. Even the humble broom behaves differently depending on where you hold it. Try spinning a broom from the middle. It's fast. Try from one end. It's slow and awkward. That's the moment of inertia in action. The farther the mass is from the axis of rotation, the harder it is to spin. Spinning in the air is only half the story. The other half is sticking the landing. When the bottle hits the table, it needs to absorb the energy of the fall without tipping over. This is where its center of mass comes into play. With a 1/3 fill, most of the mass is toward the bottom. That low center of mass acts like a stabilizing keel. When the bottle lands, its weight helps it settle rather than bounce or tip. It's the same reason why a Weeble, those egg-shaped toys that wobble but don't fall down, always rights itself. The mass is low. Landing is also influenced by the material of the bottle and the surface. A flexible plastic bottle on a hard table absorbs impact differently than a stiff one on a soft carpet. Some bottle flippers even partially crush their bottles to make them more compliant, creating a spring-like effect that absorbs the impact more gently. Once again, physics is everywhere, not just in the flip, but in the thud, in the way forces are distributed, absorbed, and resolved. As with any trend, people pushed the envelope. Double flips, cap landings, flipping multiple bottles at once. All of these variations are chaos distilled into moments of precarious order. Double flips are possible. The bottle spins twice. But the physics becomes riskier. More spin equals higher angular velocity, equals less time for the water to redistribute, equals more instability. The success rate drops dramatically, but when it works, it feels like a magic trick. Cap landings, where the bottle lands upside down on its narrow cap, are even harder. They require not only perfect spin and trajectory, but also just the right bottle design. The center of mass is reversed. The point of contact is tiny, and the odds are low. But again, it's physics, just with tighter tolerances and higher demands on balance. What makes the bottle flip so interesting is not just that it's a toy or a meme or a one-time trend. It's that it quietly teaches real physics, angular momentum, mass distribution, rotational stability, and impact absorption, all without requiring formulas or whiteboards. Children who practiced for hours were, without knowing it, performing experiments in classical mechanics. They were learning what physicists study in labs and simulations, just with plastic and water. And isn't that the beauty of physics? It's not confined to particle colliders or rocket engines. It's present in the mundane. A leaf spinning as it falls, a basketball arcing through the air, or a half-filled bottle dancing its way to a perfect landing. On a larger scale, the universe itself is filled with rotational systems. Planets rotate, galaxies spin, stars wobble. The conservation of angular momentum ensures that these motions persist unless acted upon. Earth spins on its axis because of the initial rotation of the dust cloud that formed it. Nothing has stopped it, so it continues. The moon, slowly tidally locked, now shows us only one face. Another dance of rotational balance. In that sense, the bottle flip is a microcosm, a simple object tossed into the air, responding to the same fundamental rules that guide the cosmos. Physics, at its best, doesn't just explain, it reveals. It whispers that behind every viral trend or schoolyard game lies a deeper story, one of motion and mass, force and symmetry, elegance and inevitability. So next time you see a water bottle flip and land upright, don't just smile at the spectacle, appreciate the hidden mechanics. Marvel at how the sloshing water, the tumbling plastic, and the satisfying thud are all woven together by the invisible threads of physics. It's not a trick. It's a triumph of balance, motion, and the quiet genius of how things move in our world. Heat is one of the most familiar sensations in our daily lives, and yet it is one of the most mysterious phenomena in physics. We feel it on our skin from the sun, we generate it when we move, and we see its effects when ice melts or water boils. Heat is not a substance, as people once believed. It is energy, moving from one place to another. It flows from hot to cold, reshaping the world in subtle ways, driving everything from weather patterns to the life cycles of stars. Along with heat comes pressure and the phases of matter, solid, liquid, gas, and beyond, each governed by rules that reveal how deeply temperature influences reality. For centuries, the nature of heat puzzled scientists. In the 18th century, many believed in a theory called caloric, an invisible fluid thought to flow from hot bodies to cold ones. It seemed to make sense. Hot things lost heat, cold things gained it, but experiments gradually showed that heat was not a fluid, but a form of energy. This understanding came from the work of Count Rumford, Benjamin Thompson, during the late 1700s. While observing the boring of cannons, he noticed that friction from drilling produced seemingly endless amounts of heat. If heat were a substance, it should have been exhausted. Instead, it was generated by motion itself. Rumford concluded that heat must be related to the movement of particles, a revolutionary idea at the time. This insight opened the door to modern thermodynamics. We now know that heat is the random motion of atoms and molecules. The faster they move, the hotter the material feels. Temperature is just a measure of this motion. When you heat an object, you increase the kinetic energy of its particles. When you cool it, their motion slows. This microscopic perspective explains why heat changes the phase of matter. Water is the perfect example. As ice warms, its molecules vibrate more, breaking free from rigid bonds to form a liquid. Heat it further, and the molecules gain enough energy to escape entirely, becoming gas. Yet here's the fascinating part. During melting and boiling, the temperature stops rising temporarily. Energy is still entering the system, but it's being used not to increase motion, but to change the arrangement of molecules. This is latent heat, hidden energy that transforms matter without changing its temperature. The phases of matter don't stop at solid, liquid, and gas. Under extreme conditions, matter takes on exotic states. There's plasma, a superheated gas, where electrons separate from atoms, creating a soup of charged particles. Plasma makes up most of the visible universe, from stars to lightning bolts. Then there's the Bose-Einstein condensate, discovered in 1995, where atoms at temperatures near absolute zero collapse into a single quantum state, behaving as one superatom. These extremes show how heat can reshape matter into forms we never encounter in daily life. Pressure plays its own vital role in phase changes. Water boils at 100 degrees Celsius at sea level, but climb a mountain where air pressure is lower, and it boils at a lower temperature. The lower pressure makes it easier for water molecules to escape into vapor. This is why cooking pasta at high altitudes takes longer. The water never gets as hot. The opposite happens in a pressure cooker. The sealed environment raises pressure, elevating the boiling point, and food cooks faster. The relationship between heat, pressure, and phase is beautifully captured in the triple point of water, a precise combination of temperature and pressure, where water can exist as solid, liquid, and gas all at once. It's an eerie sight in the lab, ice melting into water while boiling into steam simultaneously. The triple point is not just a curiosity, it's a standard reference in physics, used to define temperature scales with absolute precision. Phase boundaries can behave strangely. Scientists have discovered materials like supercooled water, where liquid water remains unfrozen even below its freezing point, staying in a delicate, metastable state until a disturbance, a tiny vibration, a speck of dust, triggers rapid crystallization. Similarly, superheated liquids can remain liquid above their boiling points until a sudden bubble forms, releasing violent bursts of steam. These phenomena remind us that the phases of matter are not rigid categories but dynamic states dependent on energy and conditions. Heat also drives some of nature's most stunning spectacles. The shimmering of the air above a hot road is caused by convection, where hot air rises and bends light. Geysers erupt because groundwater, trapped under pressure, suddenly flashes into steam. Volcanoes spew molten rock because heat deep inside the earth melts minerals, allowing them to flow. Everywhere we look, heat shapes landscapes and life itself. The sun, our ultimate heat source, is a giant thermonuclear reactor. It fuses hydrogen into helium, releasing vast amounts of energy as light and heat. This energy travels through space, warms our planet, and fuels everything from photosynthesis to weather systems. Without the heat of the sun, Earth would be a frozen rock adrift in darkness. On a smaller scale, heat engines, from steam locomotives to car engines, harness the expansion of hot gases to do work. The physics is simple but powerful. Heat causes expansion. Expansion creates motion. Motion drives machines. The Industrial Revolution was built on this principle, turning heat into power and transforming societies. Pressure adds another layer of intrigue to heat's effects. Deep under the ocean, pressure rises to levels that seem impossible. Here, water remains liquid, even at temperatures above 100 degrees Celsius because the immense pressure prevents boiling. In these extreme environments, strange life forms thrive, defying expectations of where biology can exist. Similarly, inside gas giants like Jupiter, pressure compresses hydrogen into a metallic state, a form of matter that doesn't exist naturally on Earth. Even the air around us reveals the intimate connection between heat and pressure. Warm air expands, becomes less dense, and rises, while cool air sinks. This simple principle drives wind, storms, and ocean currents. Thunderstorms, hurricanes, and even the gentle breeze on your face all trace back to the movement of heat through air. There's also the curious behavior of water as it freezes. Unlike most substances, water expands when it becomes solid. This is why ice floats. Its crystalline structure is less dense than liquid water. Without this anomaly, lakes and oceans would freeze from the bottom up, trapping life under layers of ice. The fact that ice floats is not just a quirk. It's a life-saving property that has shaped Earth's ecosystems for billions of years. Heat can create illusions too. On hot days, distant roads appear wet due to mirages, light bending as it travels through layers of air at different temperatures. The mind interprets the bending as reflections, like water. These optical tricks are yet another reminder that heat changes not only matter, but the way we perceive it. On a microscopic level, heat is also tied to randomness. The motion of molecules, known as thermal motion, is inherently chaotic. This randomness is linked to entropy, a measure of disorder in a system. The second law of thermodynamics tells us that entropy in a closed system always increases. Heat flows naturally from hot to cold, not the other way around. This law explains why ice cubes melt in warm drinks, why fires burn out, and why time seems to have a direction. Heat and entropy are intimately connected to the arrow of time itself. When we harness heat, we're tapping into one of nature's most fundamental forces, from steam turbines powering cities to geothermal plants using the Earth's internal warmth. We've learned to bend heat to our will. Yet heat also humbles us. It spreads, it disperses, it resists confinement. Even the most efficient engines lose some energy as heat, a reminder of entropy's unyielding march. At the edges of physics, researchers continue to uncover new mysteries about heat and pressure. Materials known as superconductors can conduct electricity without resistance when cooled to near absolute zero, defying normal expectations. Others, called superfluids, flow without friction, climbing walls and escaping containers. These states, born of extreme cold, show that when heat is removed, matter behaves in astonishing ways. From the crackling of a fireplace to the boiling of a kettle, from the crushing pressure at the ocean floor to the searing heat of a star, the physics of heat and pressure is woven into everything. It shapes matter, drives motion, and sets the conditions for life itself. The next time you watch steam rising from a cup of tea or ice cubes melting slowly in a glass, pause for a moment. Inside those ordinary moments lies the same physics that governs volcanoes, planets, and stars. Heat is not just warmth, it is energy in motion, the restless heartbeat of the universe. In the heart of a quiet laboratory, two beakers are placed side by side, each filled with distilled water. Electrodes are carefully lowered in, connected to a high-voltage power supply. The switch is flipped. For a moment, nothing happens. Then, slowly, as if defying reason, a thin thread of water rises from one beaker and reaches toward the other, forming a shimmering arc, a liquid bridge suspended in mid-air. No tube, no support, just a delicate strand of water floating between two glasses, resisting gravity, held together by forces both invisible and extraordinary. This is the floating water bridge, one of the most captivating demonstrations in physics. It looks like magic. But behind the illusion lies a deep and elegant branch of science, electrohydrodynamics, the study of how fluids respond to electric fields. It's a field where classical mechanics meets electromagnetism and where liquids can twist, climb, and even hover, pulled not by strings or pumps, but by voltage alone. To understand this strange dance, we need to first remember what water is, not just a liquid, but a polar molecule. Each water molecule has a slight separation of charge. The oxygen side carries a partial negative charge, while the hydrogen side carries a partial positive one. This makes water dielectric, meaning it can become polarized in the presence of an electric field. It doesn't conduct electricity in its purest form, but it can align, stretch, and respond. When a high voltage difference is applied between the two beakers, often tens of thousands of volts, the water becomes polarized. Molecules start aligning with the electric field, but something even more interesting happens. At the water's surface, electric tension forms. The field pulls on the dipoles, causing subtle forces that act not just on individual molecules, but across the entire surface. The result is something akin to electrical surface tension, a stabilizing force that counteracts the natural pull of gravity and allows a thread of water to hold itself aloft. This effect was first observed in 1893 by the British physicist Sir William Armstrong, but it was largely forgotten until researchers at the University of Graz in Austria revisited the phenomenon in 2007. They reproduced the water bridge with modern equipment, recorded it with high-speed cameras, and began to study its properties in detail. What they found was surprising. The bridge can grow to several centimeters in length. It has a structure, a sheath of aligned molecules surrounding a slightly more fluid core. The temperature along the bridge changes as voltage increases and the shape fluctuates in real time. But perhaps the most fascinating part is that no solid structure is holding it up. The stability comes entirely from the interaction between electric fields, molecular alignment, and surface tension, a combination that defies ordinary intuition. The same principles that allow a water bridge to form also appear in more everyday technologies, though they usually go unnoticed. Inkjet printers, for example, rely on electrohydrodynamic jets, streams of ink propelled and shaped by electric fields, allowing for precise control over tiny droplets. The technique is also used in electrospraying, where charged droplets are ejected from a liquid surface and used for mass spectrometry or drug delivery systems. In some cases, electric fields can even cause a liquid to climb upward against gravity. This is known as electrowetting, where the shape and behavior of a droplet on a surface can be changed by applying a voltage. It's already used in advanced display screens and lab-on-a-chip devices. The idea that you can move, stretch, or even split a droplet without touching it simply by adjusting a voltage feels futuristic, but it's real, and it's happening in microfluidic labs around the world. In space, electrohydrodynamics may be the key to moving fluids without pumps. In microgravity, fluids tend to float and form spheres. Traditional mechanical systems struggle to guide them, but with carefully controlled electric fields, scientists can shape, direct, and manipulate fluids remotely, critical for spacecraft that need fuel, coolant, or biological fluids to behave predictably in weightless environments. The water bridge, in particular, remains a source of curiosity. It's not just a physics party trick, it challenges how we think about cohesion, tension, and the limits of classical mechanics. Researchers have debated its internal structure, measured temperature gradients, and even used lasers to study the alignment of molecules inside. It turns out the bridge's stability is due not only to the electric forces, but also to subtle thermal convection within the liquid, a self-regulating system where heating, surface tension, and electrical forces form a dynamic equilibrium. There's also something oddly poetic about seeing a liquid perform an architectural feat, holding itself aloft, connecting two separate vessels in mid-air. It hints at a world where boundaries blur, where matter responds not just to touch, but to invisible instructions. In that moment, the water seems alive, as if it were stretching, reaching, understanding the forces acting upon it. Not all liquids behave this way. Water is unique in its structure and polar nature, making it especially responsive to electric fields. Other polar liquids can form similar bridges, though with different characteristics. Non-polar liquids, like oils, typically do not. This highlights the special status of water, not just in biology, but in physics. Its molecule is tiny, yet its properties are vast and complex, lending itself to phenomena that are still not fully understood. Electric fields can do stranger things still. Under specific conditions, Taylor cones can form pointed protrusions of liquid that eject fine jets or droplets. Named after physicist Sir Geoffrey Ingram Taylor, these cones occur when electrostatic forces overcome surface tension. They're used in electrospray ionization, a technique for analyzing molecules in chemistry and biology. The ability to turn a liquid into a fine mist using nothing but electricity opens doors to high-precision applications, from nanotechnology to medicine. On a larger scale, we see similar phenomena in nature. During thunderstorms, the electric potential between the ground and clouds can reach millions of volts. Before a lightning strike, small ionized paths form, filaments of gas drawn toward each other. The tension grows until the air breaks down and current surges through. Lightning, in a way, is electrohydrodynamics on an atmospheric scale. A fluid, air, responding to electric potential, forming bridges of its own, though far more violent. Yet the floating water bridge remains gentle, elegant, quiet. It doesn't crackle or explode. It holds. For as long as the voltage remains stable and the setup undisturbed, it persists. A tenuous link shaped by harmony, not conflict. The water bridge also serves as a metaphor. It connects not just beakers, but disciplines. It sits at the intersection of electromagnetism, fluid dynamics, molecular chemistry, and thermodynamics. To explain it fully, one must draw from all these areas, stitching together concepts into a cohesive understanding. Few phenomena are so interdisciplinary, and few are so visually striking. It's also a reminder that even familiar materials, like water, can behave in extraordinary ways when conditions are just right. We walk past water every day, drink it, wash with it, rarely considering its secrets. But give it a voltage, the right environment, and a little time, and it will reveal a side of itself that feels otherworldly. The next time you hold a glass of water, consider this. Within that liquid lies the potential to arc between vessels, to climb surfaces, to form jets, to rotate in space, all without a single moving part. Only fields, only energy and matter in conversation. Electrohydrodynamics is not a household term, but its effects touch everything from biology to electronics. As we move into a world of smaller devices, cleaner energy, and smarter materials, understanding how to shape and control fluids with electricity will become more important than ever. And perhaps somewhere in a quiet lab, another student or scientist will dim the lights, flip the switch, and watch in awe as water stretches toward itself. A suspended bridge glowing faintly under high voltage, whispering to the world that even the simplest elements hold mysteries beyond our grasp. Combustion is one of humanity's oldest companions, a force both feared and revered. Fire warms, cooks, illuminates, and destroys. We're used to thinking of it in grand, obvious forms. The crackling of logs, the glow of a campfire, the roar of a rocket engine. But sometimes the most surprising truths about fire are found in its smallest details. Tiny particles, nearly weightless, can ignite with explosive fury. A fine dust, seemingly harmless in your hand, can become a flamethrower when dispersed into air. This is the strange and striking world of surface area-driven combustion, where physical geometry becomes just as important as chemistry. It's a place where physics makes flames dance faster, hotter, and with more danger than you'd expect. Take cornstarch, for example. In your kitchen, it's powdery, soft, and perfectly safe. You can eat it, you can toss it into a bowl. Nothing about it screams danger, but throw a handful into a candle flame. Not all at once, but dispersed through the air as a fine mist. And you'll witness a bright orange fireball erupt into the room. It's startling, mesmerizing, and it's not magic. It's surface area. When a substance burns, it undergoes a rapid chemical reaction with oxygen. This reaction releases heat, light, and gases, the hallmarks of fire. But the speed and violence of that reaction depend not only on the material but also on how much of it is exposed to the air. The more surface area in contact with oxygen, the faster the reaction can proceed. A solid block of cornstarch burns slowly, if at all. The interior is shielded from the air, but grind it into powder, scatter it into the air, and every tiny grain is exposed, completely surrounded by oxygen. Ignite that, and the reaction doesn't crawl, it races. The result is what's known as a dust explosion, and it's not limited to cornstarch. Fine powders of flour, sugar, coal, aluminum, even powdered milk, all share this property. On the floor or in a bag, they're stable. But suspended in air, in the right concentration, they become combustible clouds, capable of creating explosive pressure waves and devastating blasts. This phenomenon isn't just a lab curiosity or a magician's trick. It's a serious hazard in industries around the world. Flour mills, sugar processing plants, and grain silos have all experienced tragic explosions caused by the perfect storm of fine particles, confined spaces, and a small ignition source. One of the most infamous examples occurred in 1878 in Minnesota. The Washburner Mill, then the largest flour mill in the United States, was completely destroyed by a flour dust explosion. The blast leveled the building, killed 18 workers, and led to widespread reforms in industrial safety. Similar disasters have followed in aluminum plants, coal mines, and food processing facilities. And yet, in miniature, the same physics creates the cornstarch flamethrower, a popular demonstration in science shows. A narrow tube is filled with cornstarch, and the demonstrator blows sharply into it across a flame. The resulting cloud bursts into a spectacular fireball, safe when controlled, instructive when understood. It's one of the most dramatic illustrations of how surface area can turn something benign into something ferocious. The underlying physics is simple but profound. A single grain of cornstarch has very little mass, but in a dust cloud there are thousands, even millions, of grains suspended and separated. Each one is a miniature reaction waiting to happen. The fire spreads not just from grain to grain, but through the very air between them. The reaction becomes self-sustaining, creating a chain of ignition that rapidly expands, consuming the air's oxygen and generating a shock wave. The speed at which the flame front moves through such a cloud is astonishing, often over 1,000 meters per second. In confined environments, this rapid expansion can cause devastating overpressure, shattering walls, and igniting secondary fires. What begins as a tiny spark can engulf an entire warehouse. Why does dispersion matter so much? Because when you disperse a substance, you increase its reactive surface. Imagine lighting a log on fire. It takes time, but now imagine lighting a pile of sawdust, the same material, but in tiny pieces. It catches instantly. The principle applies to any combustible material. The finer the particles, the faster they burn. This is the reason why kindling is used to start fires, and why firefighters fear fine fuels. Beyond industrial safety, this principle has found its way into fireworks, pyrotechnics, and propellants. Metal powders, like magnesium or aluminum, are often used in fireworks because their high surface area leads to bright, energetic reactions. They don't just burn, they dazzle. But there's another layer to this story. Fluid dynamics. When a cloud of particles is suspended in air, it becomes a two-phase mixture, solid and gas moving together. The particles influence the flow of air, and the air influences the movement of particles. As the fire ignites, hot gases expand, pushing the cloud outward, creating turbulence, which mixes the fuel and oxygen even better. This positive feedback loop is what makes dust explosions so sudden and violent. To predict and control these effects, scientists model the process using Navier-Stokes equations, the complex mathematics of fluid motion. combined with thermodynamic equations for combustion. It's a challenging field, filled with non-linear interactions. Tiny changes in initial conditions can lead to vastly different outcomes. In many ways, studying dust explosions is like studying chaos itself, where sensitivity and unpredictability reign. Even outside industrial environments, this physics is all around us. Campfires flare up when powdered spices like paprika or chili powder are tossed into the flames. Thermobaric weapons used in warfare exploit similar principles, dispersing a fine aerosol of fuel into the air and igniting it to produce devastating overpressure waves. The science is the same, only the scale changes. Combustion also reveals strange behaviors at the boundary between flame and surface. A candle flame, for example, has distinct zones: a blue base where fuel vaporizes, a dark inner cone, and a bright outer region where soot particles glow. These structures result from temperature gradients, oxygen availability, and chemical pathways. And even in a candle, surface area matters. If you take a candle and cut the wax into thin shavings, they will burn faster than the intact candle. Powder them, and the combustion becomes even more rapid. Again, geometry governs chemistry. In classrooms and science museums, educators use cornstarch and flame not just to entertain, but to teach. The spectacle grabs attention, but the takeaway is deeper. How things burn depends not only on what they are, but on how they are shaped. The knowledge has practical implications. Firefighters train to recognize dust hazards. Engineers design ventilation systems to prevent particle accumulation. Chemists formulate fuels with specific particle sizes to control burn rates. Astronauts plan for combustion risks in low gravity, where particles behave differently and flames can spread in unfamiliar patterns. In space, combustion becomes even more mysterious. Without gravity to pull hot air upward, flames form spheres instead of teardrops. Diffusion becomes the main method of oxygen delivery. This changes how fire behaves, often burning more slowly, with cooler, more complete combustion. Dust explosions in microgravity are the subject of ongoing research, helping to ensure safety on the International Space Station and future missions to the Moon or Mars. As we explore deeper into science, even the concept of ignition itself becomes richer. Not just a spark, but a threshold, the minimum energy required to initiate sustained combustion. That threshold depends on pressure, temperature, particle size, and oxygen concentration. It's why some fires smolder, others flare, and some never start at all. And it's why a pinch of cornstarch in a closed room with poor ventilation could become deadly, while a handful tossed in open air becomes a fleeting fireball, thrilling, harmless, and gone in a breath. The lesson here is that physics doesn't just describe what materials are. It describes what they can become, depending on how we arrange them, how we treat them, and what we understand about their behavior. In the end, combustion is not just about heat and light. It's about structure, timing, energy, and the invisible laws that govern transformation. A powder becomes a fireball, a spark becomes a storm. And the same force that warms our hands can, under the right conditions, shake buildings. So the next time you see a demonstration of dust in flame, whether it's a controlled science show or a cautionary video from industry, look past the fireball, see the invisible air currents, the molecular collisions, the vast, invisible network of surface area waking up all at once. Physics isn't just in the burn, it's in the preparation, it's in the arrangement. And when the moment comes, when fuel and oxygen and energy all align, it's in the transformation, brief, brilliant, and governed by laws that never fail. Sound surrounds us, fills our lives, and yet often goes unnoticed, not as noise, but as a phenomenon, a whisper, a heartbeat, the gentle creak of wood as a house settles. We live in a world in motion, and wherever there's motion, there's vibration, and wherever there's vibration, there's sound. Sound is, at its essence, a mechanical wave, a rhythmic disturbance that travels through a medium, whether air, water, or even solid rock. Unlike light, which can move through the vacuum of space, sound needs something to travel through. It's a wave that rides on matter, carried by the push and pull of atoms and molecules nudging one another like a vast invisible crowd passing along a signal. The beauty of this process lies in its simplicity. Tap your finger on a table, the surface vibrates. These vibrations cause tiny compressions and expansions in the air nearby. These pressure variations travel outward in all directions, a longitudinal wave, until they reach your ear. There, the eardrum begins to vibrate in sync, converting the mechanical wave into electrical signals that your brain interprets as sound. What's remarkable is how finely tuned our senses are. The human ear can detect pressure variations as small as a billionth of an atmosphere, a whisper in a quiet room. Just a few air molecules moving rhythmically is enough to set our hearing in motion. But behind that sensitivity lies deep physics. Every sound has frequency measured in hertz, which is simply how many times per second the wave vibrates. Low frequencies produce deep, rumbling sounds. High frequencies yield sharp, piercing tones. Our ears can typically hear between 20 Hz and 20,000 Hz, a range that narrows with age. Dogs and bats go far beyond that, into ultrasonic realms we can't even sense. Just as important as frequency is amplitude, how strong the vibration is. This determines loudness. A gentle vibration produces a soft tone. A powerful one, like a jet engine, sends waves crashing through air, rattling windows and bones alike. Yet loudness is not linear. It's measured in decibels, a logarithmic scale. Each increase of 10 decibels means a sound is 10 times more intense. This is why a 100 decibel rock concert feels 1,000 times more powerful than a 70 decibel conversation. But there's another property of sound that brings it to life: resonance. This is where physics becomes almost musical. Resonance occurs when a vibrating system is driven at a frequency that matches its natural frequency, the pitch it prefers to vibrate at. When this happens, the system responds dramatically, with large amplitude oscillations. It's why a singer can, in theory, shatter a wine glass. The glass has a natural frequency. If the singer's voice matches it just right, and with enough intensity, the glass vibrates more and more until it fractures. Instruments are built on resonance. A guitar string on its own makes only a faint sound, but stretch it over a hollow wooden box, and the box resonates with the string's vibrations, amplifying the sound. A violin's body, a piano's frame, a trumpet's tubing. Each one is carefully crafted to support and enhance specific frequencies. The same principle appears in architecture. Long bridges and tall buildings have natural frequencies, and if winds or footfalls match them, dangerous oscillations can build. The infamous case of the Tacoma Narrows Bridge in 1940 illustrates this vividly. A relatively steady wind caused the bridge to enter resonance with its own structural frequency. It twisted and swayed, dramatically and violently, until it tore itself apart. The footage is haunting, a reminder that even massive structures can be brought low by invisible waves. In daily life, we encounter resonance all the time, often without realizing it. The humming of a refrigerator, the ringing of a bell, the way your car dashboard vibrates at certain speeds, these are all signs that something is being excited at its resonant frequency. Even our voices work this way. The vocal cords vibrate, but it's the shape of our mouth, throat, and nasal passages, our own internal resonant chambers, that give each voice its unique timbre. One of the most delightful demonstrations of resonance is the singing wine glass. Run a wet finger along the rim of a glass, and you'll hear a clear tone emerge. What's happening is friction between the finger and glass causes periodic sticking and slipping, inducing vibration. The glass begins to resonate at its natural frequency, and the surrounding air carries that sound outward. The physics of sound also shows up in more abstract ways. For instance, sound travels at different speeds in different materials. In air at room temperature, it travels at about 343 meters per second, but in water, it's over 4 times faster. In steel, even faster still. This is because the atoms in denser materials are closer together, allowing vibrations to propagate more efficiently. This difference in speed has practical uses. Sonar, for example, works by sending sound pulses through water and timing how long it takes for echoes to return. It's how submarines navigate in the deep sea and how oceanographers map the sea floor. On land, seismic waves from earthquakes follow similar rules. Geologists can tell what's beneath Earth's surface by analysing how fast these waves travel and where they bend, a form of planetary echolocation. Some of the most fascinating aspects of sound involve interference and standing waves. When two sound waves meet, they can interfere constructively, amplifying each other, or destructively, cancelling each other out. This leads to beats, the rhythmic pulsing heard when two similar frequencies are played together, often used by musicians to tune instruments. Standing waves occur when a wave reflects back on itself, creating stable regions of constructive and destructive interference. This is how wind instruments work, by creating standing waves inside tubes. The length of the tube determines which wavelengths fit and, therefore, what note is played. Our voices, too, are shaped by standing waves. The length and shape of our vocal tract define which resonant frequencies, called formants, are emphasized. These formants give vowels their characteristic sound. It's why we can recognize speech, why each language has its own musicality, and why two people saying the same word sound entirely different. Then there's acoustic levitation, a phenomenon where objects can be suspended in air using only sound waves. By generating intense ultrasonic standing waves, researchers can create pressure nodes where small particles float, held up by nothing but the push of invisible waves. It sounds like science fiction, but it's been used to levitate droplets, manipulate materials in zero-contact environments, and may have applications in drug delivery and microfabrication. At the edges of sound lies infrasound and ultrasound, frequencies below and above human hearing. Infrasound, below 20 Hz, can travel vast distances and is used by animals like elephants and whales to communicate across miles. Some theorists believe infrasound contributes to feelings of unease in haunted houses, long waves interacting with the human body in subtle, unsettling ways. Ultrasound above 20,000 Hz finds countless uses. It's used in imaging, bouncing high-frequency sound waves off internal organs to create sonograms. It's used in cleaning. Ultrasonic baths shake dirt from tiny crevices. It's used in navigation, manufacturing, even in pest control. But perhaps the most surprising truth about sound is this: it has the power to shape matter. Cymatics is the study of how sound vibrations influence physical materials. When fine sand is sprinkled on a vibrating plate, it arranges itself into intricate patterns, geometric, beautiful, and precise. Change the frequency and the pattern changes. Sound is sculpting matter. There's a sense of wonder in this, that something as ephemeral as a wave can give form to the physical world. Sound can break glass, it can soothe, it can map the ocean floor, move objects without touching them, even shape what we see. It is the meeting point of vibration and meaning, physics and perception, and it all begins with motion, with something somewhere vibrating. The next time you hear the low thrum of a car engine, the resonance of a cello, or even the rhythmic hush of your own breath, remember that sound is not just a sensory experience. It's a physical event, a ripple through space, governed by laws, shaped by matter, and etched into memory. Vibration is everywhere. It is the quiet heartbeat of the universe. We feel it more than we realize, and every sound we hear is a reminder that even the silent air around us is never truly still. There's a quiet truth about the universe that most people, even now, have not fully absorbed, a truth that reshaped modern cosmology in a single discovery. For centuries, we believed the universe was either static or slowly coasting through time, its motion gradually slowing under the pull of gravity. But then, at the close of the 20th century, astronomers found something so unexpected that it still unsettles scientists to this day. The expansion of the universe is not slowing down, it's speeding up. This revelation didn't come from particle accelerators or theoretical equations, it came from light, ancient light, stretching across the cosmos from the distant past, and it came from stars that had died long ago in violent, beautiful explosions, type 1a supernovae. These stellar detonations, when they occur, are remarkably consistent in brightness. They are cosmic lighthouses, burning with nearly identical intensity regardless of where they appear in the universe. This makes them perfect standard candles, tools for measuring cosmic distances. By comparing their observed brightness with their expected luminosity, astronomers can determine how far away they are. In the 1990s, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to use these stellar explosions to map the expansion history of the universe. They assumed the results would show what everyone expected. That expansion was slowing down due to the mutual gravitational pull of galaxies over time. Instead, what they found was that distant supernovae were dimmer than they should be, not just a little, but significantly. This meant those galaxies weren't as close as expected. The only explanation: they were moving away from us faster than anticipated. The universe was not coasting. It was accelerating. This was not a small adjustment. It was a paradigm shift. It meant that some unknown force or energy was acting against gravity, pushing the universe apart faster and faster as time went on. Something invisible, something vast, something we had never accounted for. It was named, almost reluctantly, dark energy. The name itself reveals our ignorance. We call it dark, not because it's evil or ominous, but because we don't know what it is. It doesn't emit light. It doesn't interact with matter in any conventional way. It fills all of space, seemingly constant, omnipresent, and yet escapes direct detection. And it's not just a footnote in cosmic history. Dark energy is estimated to make up nearly 70% of the total energy content of the universe. That's more than all matter, dark and ordinary, combined. It dominates the evolution of the cosmos, dictating its fate, and yet we only discovered it about 25 years ago. To grasp the scale of this mystery, we need to go back to the early universe, to the Big Bang. After that colossal birth event, the universe began to expand, stretching space itself. Galaxies formed as matter clumped under gravity. Over billions of years, these galaxies pulled on each other, slowing the expansion. That was the picture until the late 1990s. But with the discovery of acceleration, a new force entered the scene. One that doesn't attract, but repels. One that doesn't diminish with distance, but remains constant, or possibly even grows stronger, as space expands. Where does this energy come from? The simplest explanation is something known as the cosmological constant, first introduced by Einstein in 1917. At the time, he believed the universe was static, so he added a mathematical term to his equations of general relativity, a kind of anti-gravity that balanced out the attractive force of matter. Later, when Hubble discovered that the universe was expanding, Einstein famously called the cosmological constant his greatest blunder. He didn't realize that a dynamic universe made his term unnecessary, or so it seemed. Now, a century later, the cosmological constant has returned, not as a mistake, but as a possible explanation for dark energy. According to this model, empty space itself has energy. Even in a perfect vacuum, space is not truly empty. It seethes with quantum fluctuations, particles popping in and out of existence, virtual energies that ripple across the void. This vacuum energy could create a constant outward pressure, stretching space itself. But here's where the story becomes more puzzling. When physicists calculate the expected vacuum energy from quantum field theory, the math that governs particles and fields, they get a value that's 100 billion times larger than what's observed. That's a 1 followed by 120 zeros. The most massive discrepancy between theory and observation in all of physics. If the vacuum energy were truly that large, the universe would have exploded into nothingness long ago, so we're left with a mystery. The cosmological constant fits the data, but its theoretical justification seems flawed. Alternative explanations abound. Some propose that dark energy is not constant, but changes over time, a dynamic field dubbed quintessence, evoking the fifth element of ancient philosophy. Others suggest modifications to gravity itself, that Einstein's equations might need tweaking at the larger scales. Still more radical theories invoke extra dimensions, brains, or interactions with parallel universes. Each of these models attempts to answer one central question. Why is the universe accelerating, and what is the true nature of the force behind it? Meanwhile, astronomers continue to gather data. Surveys like the Dark Energy Survey, DES, and the Euclid Space Telescope, launched by the European Space Agency, aim to map billions of galaxies, looking for subtle patterns in their distribution and motion. These cosmic maps are like fingerprints, traces of how structure forms in a universe driven by dark energy. One technique used is baryon acoustic oscillations. ripples in the distribution of galaxies left over from sound waves in the early universe. Another is gravitational lensing, where the bending of light by massive objects reveals the presence of invisible energy shaping space itself. And then there's the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this primordial light hold clues to the universe's early expansion and to how that expansion has evolved over time. Data from missions like Planck and WMAP have been instrumental in refining our models, painting a picture of a flat universe, expanding under the influence of something we still can't quite define. What's striking is how recent all of this is. The idea of an accelerating universe, now foundational to modern cosmology, was completely unknown just a few decades ago. It is a reminder that science, even at its most advanced, is still a work in progress. We are still learning what kind of cosmos we live in, and it's humbling. For all our technology, for all our equations and simulations, we still don't know what most of the universe is made of. Dark matter makes up about 25%. Ordinary matter, the atoms of stars, planets, and people, only about 5%. The rest is dark energy, a vast invisible pressure pulling space apart, accelerating the expansion of all things. What does this mean for the future? If dark energy remains constant, the universe will continue to expand forever, faster and faster. Galaxies will drift apart until they can no longer be seen. Stars will burn out. Black holes will evaporate. Eventually, only cold, empty space will remain, a fate known as the heat death of the universe. If dark energy strengthens over time, even more dramatic scenarios unfold. Some models predict a big rip, where the accelerating expansion becomes so violent that it tears apart galaxies, stars, planets, even atoms, ending the universe not in fire or ice, but in disintegration. But it could also fade. If dark energy is not constant but decays over time, the expansion could slow, even reverse. Gravity could take over once again, pulling the universe inward in a big crunch, leading possibly to another Big Bang, an eternal cycle of death and rebirth. We don't yet know which path the universe will take, but we do know that something immense is at work, a quiet, powerful force woven into the very fabric of space, a force that moves galaxies, stretches time, and determines the shape of everything to come. And it all began with distant supernovae, silent explosions that lit up the past and revealed the future. The universe is not just expanding, it is accelerating, faster every moment, and the more we learn, the stranger it becomes. Physics begins with a simple question. Why does this happen? Why does a ball fall, a flame burn, a sound echo, a leaf float downstream? These questions seem small, almost childlike, but follow them far enough and they open into the vastness of the cosmos. The journey we have taken, through floating ships, friction's quiet grip, spinning bottles and fiery dust clouds, into sound's resonant waves, and finally to the accelerating expansion of the universe, reveals something remarkable. Physics is not a set of abstract equations on a board, it's the hidden language of reality. Every event, no matter how ordinary, carries traces of this language, waiting to be noticed. What's fascinating is how physics blends two seemingly opposite qualities, simplicity and complexity. At its heart are simple laws: Newton's motion, Archimedes' buoyancy, conservation of energy, relativity's geometry of space and time. But the world built from these laws is infinitely intricate. A snowflake forms from simple rules of crystallization, yet no two snowflakes are the same. Dust dances in the sunlight, following fluid dynamics so complex that even supercomputers struggle to model it. The universe itself expands under a few fundamental forces, yet gives rise to galaxies, stars, life, and thought. As we explore these phenomena, we find patterns repeating across scales. The same physics that stabilizes a water bottle mid-flip governs the rotation of planets. The same principles that shape a candle flame describe the fusion fires of the sun. There's a unity to it, a harmony in the laws of nature that feels almost poetic. And yet, for all that we understand, there are vast regions of mystery. Dark energy, invisible and dominant, drives the expansion of the universe. Dark matter holds galaxies together, though we cannot see it. At the smallest scales, quantum mechanics reveals a world where particles blur into waves, where outcomes are probabilistic, where observation itself seems to play a role. Physics answers so much, and leaves us with questions even deeper. It's in these questions that philosophy enters. Physics is not just about measuring, predicting, and controlling. It's about wonder. It asks us to reconsider what we think we know about reality. Take time, for example. We experience it flowing, moment to moment. But relativity shows that time is not universal. It bends and stretches with motion and gravity. There is no single now across the cosmos. Every point in the universe carries its own clock, ticking in its own way. What does that say about our perception of the present? Or consider space. To us, it feels like a backdrop, an empty stage where events play out. But physics tells us space is not empty. It has energy, it curves, it stretches. Space itself is dynamic, alive with structure. When you look at the night sky, the light you see has travelled for millions or billions of years. You're not just seeing stars, you're seeing the past, stitched into the fabric of the present. Even something as simple as sound invites deep thought. It is a vibration carried by air molecules, tiny collisions passing along a message. But when those vibrations reach your ear, they become something else. Sensation, emotion, memory. A melody is physics turned into feeling. The same wave equations describe a violin's strings and a whisper between friends, yet the experience they create is profoundly human. Physics bridges the material and the immaterial. It connects the tangible, forces, energies, particles, with the intangible, meaning, beauty, awe. There's also humility in physics. It reminds us that our intuitions are not always reliable. We once thought Earth was the center of the universe. We thought time was absolute. We thought empty space was truly empty. Every generation peels back another layer, only to discover that reality is stranger, richer, and more intricate than we imagined. But physics also reassures us. It shows that there is order even in chaos. The laws of nature hold everywhere, from the smallest atom to the largest galaxy. They do not falter. They do not change capriciously. In a universe that can feel overwhelming, this constancy is a quiet comfort, and it gives us perspective. Consider the accelerating universe. We are tiny, on a planet circling a star in a small arm of an ordinary galaxy, one among hundreds of billions. Yet we have figured out, with mathematics, with observation, with curiosity, that the universe is not only expanding but doing so at an increasing rate. We have measured something that spans tens of billions of light years, from a tiny rock spinning in space. That is extraordinary. The more we study physics, the more we see that we are part of the universe, not apart from it. The same particles that form distant stars form our bodies. The same forces that shape galaxies shape our every movement. When you throw a ball, when you ride a bicycle, when you skip a stone, you are echoing the laws that govern the cosmos. You are, in a very real sense, made of the same patterns you study. And so physics becomes not just a science, but a philosophy of connection. It shows us that nothing exists in isolation. Every force is balanced by another. Every motion affects something else. Every event is linked to countless others across space and time. Conservation laws of energy, momentum, charge are not just technicalities. They are principles of harmony. Even uncertainty has its place. At the quantum level, we can never know both a particle's position and momentum exactly. This is not a flaw, but a feature of reality itself. It suggests that unpredictability is woven into existence, that the universe is not a clockwork but a living interplay of probabilities. And yet, from this uncertainty, order emerges. The classical world, where things seem solid and predictable, arises from a quantum world where nothing is ever certain. There's a lesson there. Stability does not require perfection. It grows from fluctuations. The physics we've explored in this journey, from the forces that hold ships afloat to the mysterious energy accelerating the cosmos, all converge on one thought. Reality is layered. It is simple at its core and infinitely complex in its expression. It is mechanical and yet, in its beauty, almost poetic. Perhaps the most striking aspect of physics is how it transforms the ordinary into the extraordinary. A floating leaf, a spinning bottle, the hum of a violin string. These are not just everyday things. They are manifestations of universal laws. They are evidence of patterns that stretch across scales, from the smallest ripple to the farthest star. And perhaps this is why physics feels so deeply human. It starts with curiosity. It grows with observation. It thrives on questions. It teaches us to see, really see, the world, not just as it appears, but as it is. The last step of this journey is not a conclusion, but an opening. The more we learn, the more we realize how much remains unknown. Dark energy, quantum gravity, the ultimate nature of time. The questions grow larger even as our answers grow more precise. And that's as it should be. The universe is vast. Our understanding is a candle in the dark, small but bright, growing brighter with every discovery. Each experiment, each observation, each moment of insight pushes the light a little further. The next time you watch a balloon drift into the sky, or hear the soft crackle of a fire, or look up at the stars, remember, physics is there, whispering its secrets, not to intimidate, but to invite, not to close the mystery, but to deepen it. We are not outside observers of this universe. We are part of it, made of the same fabric, subject to the same laws. We are the universe, learning about itself. And in that thought, there is something profoundly calming, something that makes you want to breathe a little slower, look a little longer, and simply marvel at how astonishing it is that you are here, in a world governed by laws that make sense, in a cosmos that invites you to wonder. And so, as our journey through physics comes to an end, take a moment to let it settle. The laws we explored are not distant theories. They're woven into every breath, every movement, every star above. The world is full of hidden patterns waiting to be noticed. Tonight, you've walked among them. Rest now, knowing the universe is still humming its quiet song and you are part of that melody.